And we're back with another riveting calculus lesson. Today we are talking about differentiability and continuity. We have one learning objective, and that is to determine if a function is differentiable and or continuous. A few notes before we begin. In this lesson, we will investigate the relationship between differentiability and continuity. Our focus will be to determine when a function fails to have a derivative. In order for a function to be differentiable at a point, the graph must be continuous and smooth at the point. And by the way, when we say a function is differentiable, this just means that the derivative exists or you are able to take the derivative. This is the derivative. We learned this in our last lesson. The limit as h approaches 0 of f of a plus h minus f of a all over h. And that was a general formula for wherever on the graph you need a slope. There's an alternate form of the derivative that looks like this. The limit as x approaches c of f of x minus f of c over x minus c. And that's just looking for a specific point on the graph from the get-go. So we have c, look down at the graph here, we have c and we have the scooch over point x, and we want the distance between those to be as close to 0 as possible. A function, y equals f of x, is differentiable at x equals c at a certain point if and only if the limit as x approaches c from the left of the derivative equals some number which agrees with the limit as x approaches c from the right of the derivative. So what we're looking at is this. Is the slope from the left approaching a point the same as the slope from the right approaching a point? I'm going to walk you through some derivatives that don't exist. Remember, at the beginning, I said a graph has to be smooth. This graph isn't smooth. When it hits the x-axis, it's like it's going down, and it goes doink, and then heads back up. So I often find myself saying, like, it's a doink doink. It is not smooth at all. But mathematically, why isn't it differentiable? First, let's look at what is the derivative, or the slope, as x approaches 1 from the left. So this line right here, what's the slope of that line? It's -1. Okay, what about the slope as x approaches 1 from the right? What's the slope of this line? It's 1. Is f continuous at 1? Oh yeah, it is. There's never a break or a hole anywhere. Is it differentiable at 1? No, it is not. Because the slope, f prime, from the left does not agree with the slope from the right. Therefore, there is no derivative. Another time a derivative doesn't exist is when there's a vertical tangent line. Now this graph is nice and smooth the whole way. That's lovely. However, at x equals 0, the slope is a vertical tangent line. And a vertical tangent line has an undefined slope. Let's look at that mathematically. Again, this is the alternate form of the derivative, and we need to know what happens at this point here at x equals 0. So first thing we're going to do is plug in 0 for c. Okay, because that's what we're scooching towards. And then we'll simplify our limit just a little bit. So I'm going to make this into fractional exponents. So x to the negative 2/3, or it's easier to see where we're going here if you put it as 1 over x to the 2/3. Now, if we plug in 0, a direct substitution, we get 1 over 0. You can't have a 0 on the bottom of a fraction. So this limit is undefined because it is a vertical tangent line. Another derivative that doesn't exist is a discontinuity. So here we have the graph of 1 over x plus 2 squared. Part A says, describe the derivative of f as x approaches negative 2 from the left and from the right. It says describe the derivative. That's the slope. So if we look from the left, what's happening to the slope of that line? It's going to positive infinity, right? Infinitely bigger and bigger positive slopes. What happens if we look as x approaches 2 from the right? What's happening to the slopes? Now you might want to say positive infinity again, but that's not true. The graph is going to positive infinity, but, and this is a little bit confusing, the slopes are going to negative infinity. We've got infinitely bigger negative slopes, because remember, we read a graph from left to right. So if we're reading this graph from left to right, these are all negative slopes. That's a negative slope always. Part B says, given the derivative, f prime of x equals negative 2 over x plus 2 cubed, evaluate the derivative at x equals 2. So notice up here, we were given the equation of the graph itself. Down here, we're given the equation of the derivative. So if we want to evaluate it at negative 2, well, normally we would just take negative 2 and plug it in, but that gives us a 0 on the bottom. So instead, and we kind of learned this trick a little bit in a previous lesson, we're going to look from the left, look from the right, plug in something just to the left of negative 2. That would be negative 2.1. And then we've got a negative number on the top, negative 2.1 plus 2 on the bottom. That's still a negative number, but it's super, super, super small. And a negative cubed is still negative. So we have negative divided by negative. That's going to positive infinity. And then let's look from the right. Plugging in something just to the right of negative 2, like negative 1.9. We have a negative on the top. On the bottom, negative 1.9 plus 2, that's a positive. And a positive cubed is still a positive, so we have a negative divided by a positive. The bottom's getting smaller and smaller and smaller and smaller. That's going to negative infinity. Since positive infinity and negative infinity don't agree with each other, then the derivative at negative 2 does not exist. Now this is a kind of cool thing. Differentiability implies continuity. If f is differentiable at a certain point, x equals c, then we automatically know that f is also continuous at c. So number 1 says, if a function is differentiable at x equals c, then it is continuous at x equals c, so differentiability implies continuity. That's great. Is it possible for a function to be continuous at x equals c, but not be differentiable at x equals c? Well, we saw 2 different examples of this earlier where it was continuous but not differentiable. A sharp corner, or a doink doink, and a vertical tangent line. We could also have a cusp, which looks like this. It kind of goes up and then peaks and turns back around again. So therefore, continuity does not imply differentiability. Looking at this graph, we're going to state whether it's continuous differentiable, both continuous and differentiable, or neither at the following points. First of all, x equals -8, that's right here. What do you think? Differentiable? Continuous? Neither? Both? Neither. It's not continuous, so it's automatically not differentiable. All right, continuing on our graph, we get to x equals -6. Is that continuous? Yes. Is it differentiable? Also yes. It's nice and smooth right there. So it's both continuous and differentiable. Keep going at x equals -4. Okay, so it peaks and then drops back down again. Because it peaks and drops back down again at such a quick instantaneous rate, it's continuous, but it is not differentiable. So we'll just say it's continuous. And then let's see, x equals 2. So that we're right here. Continuous, but that's like a doink doink. So not differentiable, just continuous. And then at x equals 3, well, it's not continuous. Therefore, it's not differentiable. So it's neither. For this absolute value graph, it says describe the x values at which the function g of x equals absolute value of x squared minus 5 is differentiable, and then, always a fan favorite, justify your answer. Well, looking at the graph, we're smooth, 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 but then we go doink, doink, uh-oh, and then smooth, and then doink, doink, and then smooth again. So it's those issues when it bounces off the x-axis. So where are those points? Well, the x-axis, that's when y equals 0, so we'll set the function to 0 and solve for x. So at x equals plus or minus the square root of 5, we have a problem. We're good to go up until negative root 5. Then between negative and positive root 5, we're okay. And then continuing on after positive root 5, we're okay. So mathematically, that would look like this. G of x is differentiable from negative infinity to negative root 5, between the root 5s, and from root 5 to infinity. G of x is not differentiable at x equals plus or minus the square root of 5. It has a sharp corner at these points. I'm the only one that says doink doink, so don't use that as an actual justification, please. Hey, piecewise functions, our favorite. Find all values of x for which the function is differentiable. So step 1 is to check continuity. Now, each of the pieces is continuous because they're each pretty little polynomials. But we need to check where the pieces meet. So we're going to check x equals 0 first. That's where the two pieces meet. So at x equals 0, does x plus 1 squared equal 2x plus 1? Well, you plug in 0 and check that out. We get 1 equals 1. Good to go. What about at x equals 3? Well, now we're looking at 2x plus 1 and 4 minus x squared. Those are the ones that meet at x equals 3. So we'll set those equal to each other, plug in 3, and we see that we get, 7, and that does not equal 1. So it's not continuous at x equals 3, but it is continuous up until 3. Now we're going to check differentiability. This is a little tedious, but stick with me. We know that it's not continuous at 3, so we don't even care about that. But we need to check differentiability at 0. Now remember, differentiability is the slopes from the left equaling the slopes from the right. So we'll use the alternate form of the derivative to find the slope at 0. Here's f of x minus f of c over x minus c. C being 0, that's the part that we're interested in. And then we can expand that and simplify. Now, as x approaches 0 from the left, we can just plug in 0 for x. And then you get the limit as x approaches 0 of 2. It's just 2. Now we have to check our other function, 2x plus 1. So again, we have f of x minus f of c, f of 0, all over x minus c. Expand it, simplify it, and you get 2. Again. So h of x is continuous and differentiable from negative infinity to 3 and then from 3 to infinity. And we know that from 3 to infinity is in play because this is just a smooth polynomial. Now we're going to show algebraically, using the alternate form of the derivative, why g of x is not differentiable. So we'll look at the slopes from the left, the slopes from the right, and our point of interest is x equals 1. So we have here f of x minus f of c all over x minus c. Expand, cancel, and now we'll take 1 and plug it in, and you get 2. Now we'll take our second function, just x, f of x minus f of c over x minus c. Well, those just, that's just 1, x minus 1 over x minus 1. Oh, look at this. Our slopes don't agree. So we say the limit as x approaches 1 from the left, that was 2, does not equal the limit as x approaches 1 from the right, which was 1. Graphically, we call this a cusp. There's a cusp at 1, 1. Okay, this is a great question. When you're forced to defend your answers, it's asking you if you really understand the concept. So if you're told that y equals f of x is a differentiable function at x equals 3, explain why each statement is true. A, f of 3 exists. Well, does it? Does f of 3 exist? We know that f is differentiable at x equals 3 because they told us that. If it's differentiable, then it's automatically continuous at x equals 3. So if f is continuous, then f of 3 has to exist. All right. What about the limit as x approaches 3 of f of x exists? Well, kind of the same reasoning as A. If it's differentiable, it's continuous. If it's continuous, then the limit as x approaches 3 must exist. That's the definition of continuity. Now, part C, what do we do about this one? The key to unlocking this one is as h approaches 0. Think about that. When have we seen that? Oh, the definition of the derivative. F of x plus h minus f of x all over h. And the limit as h approaches 0, and this time x is 3. So that's just the definition of the derivative at 3. And they told us it's differentiable, so we're good there. And then this last one, part D, this is as x approaches 3, f of x minus f of 3 over x minus 3. That is the alternate form of the derivative. F of x minus f of c over x minus c. Sometimes I forget to put the limit in front of it. This is the alternate definition of the derivative at x equals 3. And we do know that f is differentiable. So please be ready to recognize both the general form of the derivative and the alternate form of the derivative. That's it for now. Thank you for being here, and I'll see you next time.